The format of this session is going to be I have prepared the slides. So I will be explaining the concepts briefly, and then we will be looking at one or two representative problems based on the concepts. So these will be problems that are most common, and so this will give you a flavor of what kind of concepts are there, and it will not be very complex, but just to revise things. Okay, so let me just share my screen and then get started. I hope my screen is visible now. Can anyone confirm?
Yes, it is visible.
Yeah, okay. So this is the format of the slides. So first of all, we will have some concepts. So let's start with week zero, okay, because it was most foundational thing. Many students got frustrated with the amount of questions there was in week zero, and a lot of concepts were there. Mostly it was revision things from stats one. So it was all about what are random variables. The first part of this was very basics of statistics and probability. Then but from the perspective of statistics too, the most important part was about the random variables. What kind of distributions do they assume, right? So there we came to know about what are PMF, PDF, these kind of things. Then we learned about properties of PMF, then different kinds of random variables. So these are very basic things. Uniform random variables, what's the PMF for them, okay, and Bernoulli binomial. These things are very basic that we learned about in week zero, right? Then the most important thing to note about these random variables are what are their ranges, because many times you guys get confused about what's the range of a random variable and what kind of PMF do they have. Then we learned about more distributions. The most common and most important ones was Poisson, geometric. These were the most important ones. Apart from that, we learned also about hypergeometric negative binomial, but I don't think these were used too much later in the course. So for Poisson, I think you must have, you know, at your fingertips their PMFs and geometric also. So because these are very common things. Okay, I don't have any questions from week zero, but uh, from week one and two onwards, I will have some questions. Okay, so at any point, if you feel anything that I am speaking about, difficult to follow, you can just unmute yourself and just speak. So from week one and two, basically till week zero, we learned all about how do you deal with one random variables, what are their PMFs, how do you calculate probabilities related to one random variables, specifically one where you have discrete random variables or continuous random variables. In both of these cases, you learned how to deal with the case where there is only one random variable. But starting from week one, we started looking at multiple random variables. First, we looked at two random variables. Then we generalized every concept that we studied for two random variables to multiple random variables. For example, we look at the concept of joint PMF that only comes when you look at more than, two or more than two random variables. So uh, first we see concepts like joint, marginal, conditionals. So this was kind of the theme of week one and two, and then independence. So how do you define the joint PMF? How do you understand the joint PMF, marginal PMF, and conditional PMF when you are dealing with more than two random variables or two random variables? So here we have examples for two random variables. So we have suppose two random variables, then what's the probability of occurrence of them together. Then marginals is just you take you have one random variables, what's the probability that it will take some value? Okay, and you will add it over all the uh, possibilities of the other random variables. Then conditional PMF. So earlier what used to happen, that we had, we also learned about conditional probabilities, but not in terms of random variables, right? But now we are we started studying them in a formal way using random variables, right? So these are the things that came into the context of multiple random variables. Then we looked at the concept of independence, and in independence we see that if you have two random variables and if they are independent, then their PMF, the PMF of the joint is equal to the product of the marginals, right? So this is the property of independence. Then we also looked at a concept of I. It is not currently used, but used in week 7. Then one more important thing was there, that we have a geometric random variable. It has a memoryless property, and memoryless property means that suppose you have a random variable x which is geometric, it has already taken value greater than m. Then what is the probability that it will take value greater than m plus n? So it will not be affected by m. So what does it mean essentially is that doesn't matter whatever has happened, the occurrence of future probabilities will not be dependent on whatever has happened already, right? So probability of x being greater than n plus n is just probability of x being greater than n. We are not affected by the thing that x has already taken value greater than n, right? Then we looked at a concept of independent random variables, sorry, sum of independent random variables. So suppose you have two random variables x plus y, and you want to calculate the probability that z takes some value y. X has some range, it can have some range, so it has a discrete range 0 1 2, and y has some discrete range 3 4 5. So suppose you want to calculate the probability that z takes value 5. So how do you do it? You first you take one random variable, okay, and you iterate through all of the possible values of x and y for which this value of the sum can be taken. So this is how you calculate the sum of independent random variables. Then we had a very very important property called convolution, which was related to two independent Poisson random variables. Okay, so we had many problems also in the lectures also, and then in the activity questions and EAs and GAs also. So what essentially this had was that if you have two random variables x and y, these follow Poisson distributions with lambda 1 and lambda 2 parameters. Then if you add both of the Poisson random variables, z equals x plus y, it will follow a Poisson lambda 1 plus lambda 2. So this looks like a very very simple thing, but while you are solving a problem, it can have uh, very simplifying uh, significance.
So this property is specific to Poisson only, right?
Yeah, Poisson only, and only when these are independent.
Okay.
Yeah. Then we looked at a concept called CDF that you have been looking from stats 1 days. So CDF is just the probability that a random variable will take values less than or equal to some value. Okay. So this was all uh, about all of the concepts that we saw in week 1 and 2. So here we saw related to just two random variables, but we had other examples of multiple random variables. So suppose you want to you want to calculate the joint PMF of more than two random variables. Okay, if they are independent, it will be the product of the marginal PMFs or of all the random variables. Then you have marginal PMFs. So if you had three random variables, for example x, y, z, then you could have uh, marginal PMFs for x, y, and z. Okay, then when you consider conditional PMF, then you know, you could have multiple kinds of conditional PMFs. For example, uh, you could condition over, you could have the probability of x equals something and y equals something, small y, given z had taken some value. So you can take any combination of these three random variables and put them in the condition or in the point where you are trying to calculate the probability. So I hope all of these things are, you are finding very easy, because these were very basic things that we discussed in the start of the course. Then, yeah, this is one question related to week 1 and week 2. So we have two four-sided pair dice are rolled. It's not six-sided. If the sum of the numbers on the two dice is less than or equal to 7, then find the condition probability that the number on the first die is 4. So this is just like the case where I discussed about sum of independent random variables. So first of all, how do you deal with such problems? You define random variables corresponding to different experiments or different events in the experiment, and then you first step is to write it in probability notation, right? So you have to calculate the probability that the number on the first die is 4, given x plus y is less than or equal to 7. Sum on the numbers on the two dice is less than or equal to 7. Okay, then x then conditionally it's simply equal to the probability of joint divided by the condition, the probability of the condition over which it is conditioned. So we are conditioning over x plus y less than or equal to 7. So we put that in the denominator, and then what we put in the numerator, we put the joint of x equals 4 and x plus y less than or equal to 7. So it will correspond to only three cases. So x is already equal to 4, so y can take values, uh, you know 2, 1, and 3 when x plus y less than or equal to 7. And similarly here, since x plus y can take values only up to 8, x plus y less than or equal to 7, we can write it as a complement 1 minus probability x plus y greater than 7. Okay. So since it is a fair die, it will have the same kinds of probability calculations that we have for a six-sided fair die. So you can do these calculations very easily, and you will find the answer is 0.2. I hope it is not confusing. Okay. Then we discussed about week 1 and week 2. Then we start with week 3. Wait a second. Okay, so we started week 3 with the main concept being expected value and related properties. So what is expected value? It represents the center of a random variable, right? And it is related to mean. Okay, it is essentially mean that you have been studying from previous classes. But here we learned about some new properties of expected value. It was linearity. So when you have a random variable, you multiply it with some, you create a new random variable. So you have a new random, you have a random variable x. Now you multiply that random variable to get a new random variable y equals cx. Then its expected value will just be equal to c times the expected value of x. So this was linearity, and this also holds here. Okay. And one very important, this was very important in my opinion. If x and y are independent random variables, then then the expected value of product of the random variables is equal to the product of the expected values. So this is very important, I would say. Then this expected value of a function, it was also very important. So what's the very neat thing about this expected value of a function is that, suppose you have a random variable x1 to xn, multiple random variables, or even one random variable, does not matter. you have got a function y equals some function of the random variable x, and you want to calculate the expected value of y. So for calculating the expected value of y, you need to know the distribution of y, right? You need to know the distribution of y. But this method, in this method, you can calculate the expected value of y without knowing the distribution of y. So what are we using here? We are using fx1 to fxn. This is essentially the distribution of or PMF of x, right? So we are using the PMF of x or the distribution of x, information about the distribution of x, to calculate the expected value of y. So we just need to multiply the function times this. So suppose I will give you a concrete example. Suppose we have a random variable x. So it takes value 1, 2, 3, right? With equal probabilities 1 by 3, 1 by 3, 1 by 3. Okay. Then we have another random variable y equals x squared. Now we want to calculate the expected value of y. So we can always square it, find the probability of so what are the values that y can take? Y can take values 1, 4, 9. Okay, so it will in this case also take, so let's make it a little, okay, 1 by 2. So these are the corresponding probabilities. Now we have another random variable y, which is just x squared. Now we want to calculate the expected value of y. It means we need to know the distribution of y, but we can bypass that requirement and directly know the expected value of y using the information about distribution of x. So what we need to do for that? This formula says that we need to multiply the function value. For example, y takes value x squared, so 1 times the probability of x taking that value. So this is just 1 by 4. Then plus 2 times or 4 times 1 by 4 plus 3 squared 9 times 1 by 2. So you can see how powerful this simplification, how powerful this formula is, right? So this was very important. Then we have variance of, then we discussed about variance. So variance can also be represented as some expected value, right? Expected value of x minus expected value of x. So yeah, then we had a simple formula. Variance of x is equal to expected value of x squared minus expected value of x whole squared, right? So it also had some properties. So when a scaling the if you scale a random variable by a, then it will come out as a squared. So it will become a squared times variance of x. And when you're translating it, the variance does not change. Then standard deviation has had a similar property, similar to variance, because it is just square root of this. So these are very simple things. Then we discussed about standardized random variables. You just you have a random variable, you subtract its mean divided by the standard deviation. It becomes a new random variable which has a variance 1 and expected value 0. So this was all about week 3. And yeah, there was a second part of week 3 where we discussed about covariance. So covariance you have also studied in stats 1, but here we discussed in terms of random variables. It just describes the kind of association two random variables have, okay, two or multiple random variables have. And if their covariance is 0, it means they are independent. Okay, sorry, if there was one important thing here. If their covariance is 0, what does it mean? It means they are not correlated. So I think here there is a misunderstanding. So this statement is not fully correct. So when two random variables x and y are uncorrelated, it does not mean, okay, that they must be independent. But if two random variables are independent, then they must be uncorrelated. So this was a simple property that we studied. Then correlation, this thing you also know, it kind of measures how much is the association between two random variables. Then two very important inequalities that we studied were Markov's inequality that was there for a non-negative random variable, and we had a Chebyshev's inequality. So the purpose of these two inequalities was that sometimes we are not interested in finding the exact probability of a random variable taking some value, but instead we are interested in finding that how much a random variable can take a value. So uh, can it take values greater than something? Will it be confined in some I mean will a random variable take a value confined to some range, or it will take values outside of a range? So when we are interested in such kind of questions, we refer to these inequalities. Okay, so if you solve some questions, you would get the idea of where it is useful. So this was very basic form of Chebyshev's inequalities, these two. So this was the upper bound and this was the lower bound, right? And actually there were more forms of the Chebyshev's inequality that just derived from this one. Okay, so we don't have much questions from week 3. Okay, and we just have one question. So it asks to calculate the variance of x and y. We have been given x and y, two independent random variables with means are given and variance is also given. We have to find the variance of x, y. So we will just use some simple properties of expected value and variance, and then we will be able to find the variance of x times y. So variance of x times y can be written by using the simple property of expected value. Sorry, the variance. It is expected value of the random variable squared minus expected value of the random variable whole squared. So since this hint is also given, if x and y are independent, then x squared and y squared are also independent. So you just multiply it to make it the expected value of x squared times expected value of y squared. Then you put the respective values, and then you will get the answer in a very simple way, just by applying the properties that we studied in week 3. Similarly, the questions related to Markov's inequality and Chebyshev's inequality are very simple, but I have not included them because later when you will see the same kind of questions related to Markov's and Chebyshev's are there in week 7, and those will get you the revision for this concept. So we don't have much time, so I didn't include much questions. Okay. Then coming to week 4, so I took the very first TA session of this September term for stats 2. I discussed about the whole structure of statistics, right? So from week 1 to week 3, we discuss about the discrete random variables. We study about multiple random variables, various properties. Then from week 4 to week 6, we discuss about continuous random variables. The same properties that we studied for discrete random variables, we discuss them for continuous random variables. From then later, when we will discuss later weeks, we will tell more about them. So in continuous random variables, first we start with the concept of a CDF, discussing about it formally. Okay, and what are the properties of CDF? Okay, how do you find the probability? So one important thing here in case of continuous random variables was that a random variable cannot take any exact value. Okay, the probability that it will take any exact value, it is 0. The continuous random variable can only take values in a range, and that is calculated by subtracting the CDF. So CDF is the foundational concept related to continuous random variables, and through that we derive probability density function by just differentiating the CDF. Right? So basically, continuous random variables are defined in terms of CDF. Okay, PDF is the later thing that we get. Okay, so these things we discussed. Then probability density function. it is just the differentiation of the CDF function, and probability of event is just integration of the PDF function for that range, right? Then we have density function. Okay, we have some properties of the probability density function. First of all, it is piecewise continuous. Okay, so we have some properties of probability density function. First of all, it is always greater than equal to 0. Okay, when you integrate it over the full range of all the possible values that it can take, it will add up to 1. And what is the support of random variable? It is all of the possible values where the probability density function, this is PDF, it is greater than 0. So uh, that area is called the support of X. Okay, so this was just the refresher on all of the properties of continuous random variables. I think these things you would have studied in Statsman also. But yeah, then these are the okay. Yeah, then we studied some more properties related to continuous distributions. Okay, so uh, we have here. Okay, so in week 4 we also came to know about some important continuous distributions that we have. So there was actually three most important distributions that we studied in week 4. The first one was continuous uniform distribution. uh, it's a PDF is equal to 1 by b minus a for x in range a and b, and CDF is simply x minus a divided by b minus a. If you integrate the PDF from the starting point to the point x, you will get this CDF, or you can do vice versa also. You can differentiate the CDF, so you can verify this by doing integration or differentiation. Then we had exponential distribution and normal distributions. So here we discussed PDF, CDF. These kind of things are very basic. These are the concepts that are used very frequently in rest of the course. Okay, so yeah. So here we have one question related to week 4. So here someone is throwing a dart onto a circular board, and we are denoting by x the distance from the center to the point where the dart hits the board. And clearly x is a continuous random variable, right? And what is the probability? Sorry, not probability. We don't talk about the probability of a continuous random variable. We talk only about the PDF. PDF is defined by this. PDF is defined by this function. Here we don't know the value of k. So we will use some properties of the continuous random variable, and we will get the value of k. That is when we integrate it over the full range of the values that the random variable can take, and we will equate it to 1. Then we will get the value of k that will come out as 6. And we'll put here the value of k. So we will have the complete information about the distribution of x. We will have the complete information about the PDF. And then using this PDF, we can calculate this required probability. So this is some simple probability of mod of x minus 0.5 less than equal to 0.25. So we can simplify this, and here I have simplified it. And then you will find that it is actually asking for probability that x will take value in the range 0.25 and 0.75. Okay, and this calculating this probability is very easy. What do? You just take the PDF function and you integrate it over integrate from 0.25 to 0.75. So this is just the integration. This is not something I need to discuss here. So you get the value this. So this is kind of a representative thing about week 4. It does not have a lot of concepts that are challenging. Then week 5, we week 5 is just continuation of week 4. We were studying about the continuous random variables. We discuss more properties of continuous random variables. For example, uh, so this thing we discussed for discrete random variables, right? So when you have a random variable x and uh, you define a function of x, y equals g of x, then how do you find the PDF of x? Sorry, PDF of y. That is a challenge. Okay. So in discrete case, we had a random variable x. We defined another random variable y in terms of x, and then we tried to find the CDF or PMF of y. Here we are trying to do the same thing. So here there was actually two methods for this. The first method was when the function that you are considering, so y is equal to g of x, it is a very nice function in the sense that it is monotonic and differentiable at every point in the support of x. In that case, what do? You have a simple formula. Okay, you just apply the formula and you will get the PDF of y. But when you don't have the function that you're considering as monotonic and differentiable at every point in the support of x, then you will have to use a longer method that was informally called the CDF method. So what do you do in CDF method? First, you try to calculate the CDF of y. So a very uh, common example that we saw was, suppose you have a random variable x and it is continuous. Now you try to find the probability. Sorry, now you consider the another random variable y equals x squared. Okay, so x is clearly differentiable at every point. So suppose x is between, so I think this was in activity questions. So the range of x is this. Then what will be the range of y? Range of y will be between 0 and 9. So clearly it is differentiable at every point, but the thing is it is not monotonic at every point. Okay, so it is once increasing, once decreasing, then increasing. So for this, we cannot find the PDF of y using this formula. So we will need to use the CDF method. For that, we will first calculate the CDF of y, and then we will try to find the PDF of y by just differentiating it. So it was a longer method. I think it was very challenging for a lot of students, but yeah, once you pay attention to it, it was not that complex. Then this was very simple. Just when you have simple functions,
Sorry to interrupt you, sir. I just want to know this formula, what you have written here.
yeah.
The G inverse, sir, Y. I'm not able to get you. What is this, sir?
Okay, so G inverse of y. So take for example this function y equals ax plus b. So this is a simple affine transformation. Okay, so
Okay.
what is G inverse of y here? It is simply y minus b by a. Is you just invert the function g. So this is g of x is equal to ax plus b. This is your function that you're trying to find the PDF of. Okay, you
Okay.
invert the
But sir,
function.
invert in
Yeah.
the sense, sir, can you clarify, sir? Because it will be 1 upon ax plus b if we inverse this function. Y.
Which
If we
function?
inverse y, sir, if y is equal to ax plus b, if I inverse y, that implies that 1 divided by ax plus b, isn't it, sir?
No. So this is not the reciprocal. Okay, so there is difference between what you are saying is a reciprocal. So if you are just taking the reciprocal of 1 by, so
Exactly, sir. Exactly, sir.
G inverse does not mean you are saying 1 by g. So this
Yeah,
is,
yeah.
I'm talking about in the sense of function inversion. Okay, so
Can you elaborate, sir? I am not able to get you this.
Yeah, so for example, if you have a function g of, or for example, f of x is equal to x squared, then how do you invert this function? Or this is equal to y, okay, y, small y, for example. How do you invert this? So f inverse of y is equal to under root y. Okay, so this is just this is the concept of function inversion that is there in class 11th, I think. So you can go back to that textbook or search about it on the internet, you will find it. So it is not talking about the reciprocal that you are saying 1 by ax plus b, but instead it is talking about function inversion. I hope that clarifies your doubt.
Okay, sir.
Yeah, so when you put all of these things here for these simple cases of a scaling and affine transformation, you will get this formula. So this is just application of this formula, but one more important thing here was this CDF method. Okay, so okay, then after knowing how do you calculate the PDF or CDF of a function of a random variable, we discussed about what is the expected value. Just it has a similar concept, just like we discussed for discrete random variable. So in case of discrete random variable, what do you do to calculate the expected value? You just multiply each of the possible values with the corresponding probabilities and then add all of them. Okay, so the equivalent of addition is integration when you have a continuous random variable. So you just integrate the uh, x times the PDF of x. So this is kind of represents the probability, but it is not exactly the probability. So x times fx of x, you integrate it over all the possible values that x can take, and you will get the expected value of x. Okay. Similarly, you calculate the variance of x. Here, this formula also holds. So expected value of x squared minus expected value of x whole squared, and you can also calculate it using integration. Okay. So you remember this? How do you calculate the expected what do you call it? Expected value of function of a random variable. Okay. So how do you do it? You remember it for discrete random variable, right? So gx times the function times fx of x, right? So function times the PMF. So here, when calculating the variance, the function you consider is x minus mu of x. This is squared. This is your function. This is your function g of x, and this is your PDF. So this is how you calculate the variance of x. Then we had similar Markovs and Chebyshev inequalities for continuous case also. It was very similar to what we did for discrete case. Then marginal density, conditional density. Okay. Here one important thing was there that we considered mixed cases where we have two random variables x and y. One of them is discrete and one of them is continuous. So yeah, so this was all about week 5. So now we will see one question, very simple question from week 5. So we have a random variable x which is uniform in the range -3 to 3, and we have to find the PDF of mod of x. So you must know what's the graph for mod of x. It is this. So it is neither differentiable at all of the at all of the values that x can take. So it is not differentiable at 0 0, and it is neither monotonic. So it is first decreasing then increasing. So we obviously we cannot use the direct formula that we had. So for this we will have to use the CDF method, right? So first we calculate the CDF of y. First we will have to use the CDF of y. We find the CDF of y is y by 3. So how do we calculate the CDF of y? We consider this random variable. So we have a random variable y, and we want to calculate the PDF of y. This is our goal. But we don't calculate the PDF first. What we do is we first calculate the CDF. So for CDF, what does CDF mean? we assume that y takes value probability, we write CDF of y as probability that capital Y, the random variable, takes value less than or equal to, okay, less than equal to, or equality does not matter in case of continuous random variable, so we can omit that. But probability that the random variable capital Y takes value less than some small y, okay. So y, small y is some value in the support of capital Y. So this is this represents the CDF of y. Okay, in place of y we will just put mod of x, the function expression for y. When we expand this, this just becomes the calculation of probability in terms of x. So what is this line asking for? This is asking what is the probability that x will fall in the range minus y and plus y. So we can calculate this probability if we know the distribution of y. To calculate this probability, we just need to know the distribution of x. So we know the distribution of x. It is 1 by 6. Okay, its PDF is 1 by 6 because it is uniform. So we just integrate between minus y and plus y. We get the CDF. And to calculate the PDF, we just differentiate it, and we will get the value of PDF. Yeah, so here was one more problem. So this was from the lectures. Okay, so here you have x, which is uniform in the range minus 3 and 1, and then you want to calculate the probability of you want to calculate the PDF of y. So first, you, in a similar way, you calculate the CDF and you consider different cases. You will have to consider different cases here because it becomes complex whenever you are using a CDF method, and it's not continuous. In that case, we will consider different cases, and you will get this is discussed in the lectures. I have just put it here for reference to this week. Okay, coming to week 6. We have we considered joint, marginal, and conditional densities. So up to week 6, we have considered we are discussing the continuous random variables. So we discussed everything related to continuous random variables, the basic concepts, CDF, PDF, expected value, inequalities, everything. But we have not considered joint, marginal, and conditional densities till now. So that's what we do in week 6. So joint density, it's simply the PDF when we consider the occurrence of both of these random variables together. Okay, and in this case, there comes the concept of a double integration. Okay, so this makes it a little challenging for some students. But yeah, this was pretty doable. So the special case, one of the special cases was 2D uniform distribution. So suppose you have two random variables, x and y, okay, and these have uniform density in some region. Then the PDF is simply 1 divided by the area of that region. Okay, I hope you remember this. And then how do you calculate marginal densities? So this was all about so the concepts that we discussed for discrete random variables were the same, but the only difference here was that the sums were replaced by integration. So how do you calculate the marginal density for any random variables? Suppose we are considering two random variables, x and y, and we want to find the marginal of x. Then we will need to add up all the joint densities, okay, all the joint densities over all the range of the other random variable y. So we this is actually constant here. Okay, so this is constant. It's obvious from here because we have considered x, and y is variable. So we will add it over all the possible values that y can take. So it will this in this way we will get the marginal density for x. Similarly, we will get the marginal density of y. Okay, and here one important piece of information was that marginals do not generally determine the joint density. This was also true for discrete random variables, right? So We saw some example there. So margins do not determine the joint density. Actually, the thing is, if you have a marginal density, okay, then what does it mean? Marginal is calculated by adding up the joint densities, right? So if you have a joint density, you will go to a unique marginal density or marginal PMF in discrete case. But if you are given marginal density, okay, then you cannot go back to joint density. Okay, no, this statement is wrong. I meant to say that if you are given marginal density, then you cannot uniquely go to the joint density. Okay, one marginal density might correspond to multiple joint densities. Might correspond to multiple joint densities. Okay, yeah. Then this was very similar to what we discussed for discrete random variables again. Here we have the concept of independence. So when two random variables x and y are independent, their joint density is equal to the product of the marginal densities. And similarly, we have described here conditional densities for this. Okay. And we have some properties of conditional density. This is just Bayes' theorem. So joint can be written as one random variable times the second random variable given the first, and in opposite way also. Okay, so this is a very typical problem of week 6. We have been given joint density here of x and y, and here we don't have any information about the value of c. So you just use the property of a continuous random variable. Here you will add it over both the values of x and y. So you will integrate over both the values of x and y, all the possible values, and you will equate it to 1, and you will get the value of c from here. But this is more interesting. The second part of the question is more interesting. Here you have to calculate the probability that x will take value 1 less than 1 and y will take value less than 3. So here you have to calculate some joint probability. So for that you will need the complete information about the distribution of x and y joint density. So you would also you have already got the value of c from this first part, okay, 1/8. So you can just put it here. So these things are must be very easy for you, I hope. So this is x goes up to 2 and y goes up to 4, okay, but only up to 0 and 2, and y goes from 2 to 4. Okay, so this is the support area for this joint density, but here it's not uniform. Okay, it's dependent on this function. So that's why we need to use integration here. Otherwise we would just have used a simple multiplication and calculation of joint density. So this was first half of the course, and then we move to week 7. So up to week 6 it was just simple calculation of probabilities and not very complex things. Okay, yeah, it was somewhat complex in terms of computation, but not theory wise. But from week 7 onwards we had more of theory and more of philosophical discussions about what kind of statistics we do and more theories, right? So in week 7 we start with the study of samples. Okay, so whenever we collect samples, we assume that it follows a certain underlying distribution. It has come from certain underlying distribution, and our goal is to understand. Our goal is to try to understand the underlying distribution using the samples. So first we started with what is empirical distribution and sample statistics. So what is empirical distribution? It is just the suppose you know that what's the when you have a fair die, what's the probability of occurrence of each of the phases. But what you do, you sample it on your own. You throw the die multiple times on your own, and you count the number of times you get one divided by the total number of times you threw the dice. So that will be kind of your empirical distribution, whatever you have experimented, and according to your experiment you have got the distribution, so that is called the empirical distribution. Then we have uh, yeah, so this point was there that as sample size increases, empirical distribution approximates original distribution. Then we had sample mean, okay, expected value and variance of sample mean. So this was all very basic things, I think. But most important point in this slide is that the expected value and variance of sample mean. So expected value of the sample mean. So it can confuse you sometimes, but you have to be able to differentiate between what is a sample mean and what is a distribution mean. Okay, so suppose we sample some die throws. We throw a die multiple times, and what we do, we have a sample. So we calculate the mean, for example, for some random variable. Then it is a sample mean, but but the mean of the distribution that the sample has come from, it is mu. Okay, so these are two are different things. And variance of x is simply sigma squared by n, that can be derived very easily. Okay, and you can see here that as we increase the sample size n, it will decrease the variance and ultimately it will become 0. Okay, so this was all about week 7. Then we had sample variance. So sample variance we already know, we have studied about it in previous classes also. So it is just you take each of the random variables and you subtract the sample mean. So here is a mistake. All of these are sample means, and you divide it by n minus 1. And expected value of sample variance is simply the distribution variance. Okay. Then we had one concept of sample proportion. So just like we have sample mean and distribution mean, so we have a concept of sample proportion. So suppose you throw the die multiple times and you calculate some empirical distribution. And when you calculate some probability according to the empirical distribution that you have got, you experiment it and you calculate some distribution. When you calculate some probability from the empirical distribution, it is called sample proportion. But probability of A is actually when you are using the actual distribution or underlying distribution, you have, then it will be the actual probability. Okay. The most important concept in week 7 in my opinion was weak law of largest. Okay, there were a lot of problems related to this within quizzes. So basically it is just application of Chebyshev's inequality on sample mean. So here one of the most important things you learn is that sample mean and sample variance, these are random variables. Okay, these are not fixed quantities. So if you sample if you take different samples, the sample means and sample variance will vary. So that's why these are random variables, not fixed quantities. Okay, and we can talk about these random variables, sample mean and sample variance, in the same way that we talk about other random variables. Okay, so what did the Chebyshev inequality tell about any particular random variable? It told that the random variable, if we subtract its mean and take it take its mod value, and probability that it will be greater than delta, it will be less than equal to, what was this? So this is simply the variance of that random variable divided by this limit, delta squared. So variance of sample mean is simply sigma squared by n. Okay, so that's where you get the weak law of large numbers from. So it is a very simple application of Chebyshev inequality to sample mean. Here we have a sample mean that is a random variable, and mu is the distribution variance, that is the expected value of the sample mean. Okay, so here we have a simple application of Chebyshev inequality. Sorry, I think no. Here we have a simple application of weak law of large numbers. So we have been given a sample, its mean is given and variance is given, and here it's clearly written that we have to use Chebyshev inequality, because I think whoever had said the question didn't want you to be confused between weak law of large numbers and Chebyshev's. But basically you are applying here weak law of large numbers. So we have to find the probability. So no, actually here we have to find the minimum value of n, such that the probability that the sample mean lies between minus 0.5 and 0.5 is at least 0.95. Okay, so as you know, sample mean, okay, sample mean is a random variable, and its variability depends upon the value of n. So if you have a large value of n, then it will be less variable. Okay, so that's why it is asking what's the minimum value of n for which it should lie between this. Okay, and the probability is at least 0.95. It means it has a very high probability of lying between these 2 points. Okay, so the main gist of this problem is to convert this in mathematical notation and then being able to use it. Okay, so it is saying that, so we will just put it here. Minimum value of n such that the probability that sample mean lies between point this. Okay, so this is the upper bound version of the Chebyshev inequality or weak law of large numbers. The corresponding lower bound is, because here we have to calculate the minimum value of n, right? So we will use probability of x minus mu less than delta will be greater than equal to 1 minus sigma squared by n delta squared. Okay, so this is at least 0.95, it is asked. So this is the probability. So what we will do, we will simply substitute 1 minus sigma squared by n delta squared with 0.95, because it is asking that it should be at least 0.95. So this is given, and then when we solve for this, we will get the value of n here, because sigma squared and delta squared, everything is given here. Okay, so this was all about week 7. Now coming to week 8, that was very, very important, and I think in end term most of the questions will be from week 8 to sorry, not week 8. I can consider week 7. Week 7 to week 12 are the most important. So it's obvious that most of the questions are from the last weeks of the course in term. So the two of the main things that we studied in week 8, one of them was moment generating functions, and the other was central limit theorem. So since no one of you have interacted for a long time, I would like to ask if everything is okay. Are you all following what I am discussing?
Yes, sir.
Yes, sir.
Yeah, okay. At any point, if you feel the need to unmute yourself, feel free to do so. Okay. Okay. So in week 8, we had two kind of concepts, central concepts. One of them was moment generating functions, and the second was central limit theorem. So what is a moment generating function? Moment generating function was simply defined as the expected value of e raised to the power lambda x. So we have a random variable x, and we consider another random variable y is equal to e raised to the power minus lambda x for some lambda. And when we try to calculate the expected value of y, this is precisely what moment generating function of a random variable is. Expected value of e raised to the power lambda x. So the main purpose of studying this was to deal with sum of random variables. Okay. So
Hello,
yeah,
is this session is recording available?
yeah. So I think it is being recorded.
They will provide us.
Yeah, definitely.
Okay, and what about these notes? Can we
Oh,
get a screenshot or PDF of
okay.
this note?
Okay, I will make some arrangement to send it to you guys.
Okay.
This slides. Okay. So we have x, that is a zero mean random variable, and the mgf of x is denoted mx for some lambda. It is equal to expected value of e raised to the power lambda x. Okay. And for a special case, when x is normal of 0 sigma squared, its mgf is equal to e raised to the power lambda squared sigma squared by 2. So it had some significant you know importance. That's why this is being mentioned here. Through this only we come to know about the center limit theorem. Okay. So, and at multiple points you may need to use the mgf of a normal distribution. So you can remember this if you want. It's important. Then for independent random variables x1 to xn, the mgf of their sum uh, is equal to the product of the mgfs. Okay. So suppose we have many random variables x1, x2, x3. Okay. We want to calculate the mgf of, and y is equal to this sum. Okay. Or s is equal to this sum. Then when we are calculating ms or the moment generating function for this sum, then what we will do, we will calculate the expected value of e raised to the power x1 plus x2 plus, sorry, yeah, x1 plus x2 plus up to xn. So you know that when we have uh, these powers added, then we can multiply this. So it will just be expected value of e raised to the power lambda. Sorry, it is lambda times this, right? So lambda times this. So we can write it as e raised to the power lambda times x1 times e raised to the power lambda times x2 up to e raised to the power lambda times xn. Okay. So now since x1 to xn are independent, okay, then e raised to the power lambda x1, these are also random variables. So these are all will be also be independent. So the expected value of the product can be written as the product of the expected value. So expected value of this times expected value of this. So this will correspond to the mgf of x1, mgf of x2. So it means we can write it as the product of the mgfs. So this was about moment generating functions. And then we had central limit theorem, that is very simple but really powerful when calculating probabilities. Okay. So it has actually two versions. So here we have one version where you use y, and then sometimes you need to use the sum version. Okay. So in place of y you use s. Okay. This is so what the central limit theorem says is that whenever you have some random variables which are IIT and you add a lot of them, then that roughly follows a normal distribution. Okay. What we have done here is simply we have standardized the random variable y, so it is following the standard normal distribution with mean mu and variance 1. Y just the summation of this. Okay. So why do we have here under root n sigma squared? Can anyone tell me? Okay. So this is just a standard deviation of S. Okay, standard deviation of Y. So this is just the mean of we are standardizing it here. So Y minus mean of Y, that is n mu, divided by the standard deviation of Y. So variance of Y is simply variance of Y, it is equal to n times variance of X, that is sigma squared. So that's why we are dividing it by under root n sigma squared. Okay, we are just standardizing it. Nothing magical is happening there. So it is very simple theorem. Then in week 8, we learned about some distribution, important distributions. For example, gamma distributions, okay, its mean variance. These kind of things are just like facts. But gamma distribution, beta distribution, Cauchy distributions. So these distributions we learned about in week 8. But more important than remembering them, the important thing is about what kind of relationships between these distributions are. So that we will see in the next slide. So here are some important results about uh, the whole of BKT in general. But the most important part here is that there is relationship between the three distributions that we saw in the last slide. Okay. So the first thing is that linear combination of normal distributions is also normal. This is the first thing, with mean being equal to the coefficient times whatever random variable. Okay. Yeah, the mean is equal to a1, the coefficient times the mean of the individual random variables, and sigma squared is this. Then here we have some important properties related to the random variables that we saw in the saw previously. So sum of n IID random variables, n exponential IID random variables is simply gamma. So these relationships are very, very important and come very handy when you are solving problems. So it is usually said that gamma random variable is kind of a generalization of the exponential random variable, right? So when you add a lot of when you add a n random variables, n exponential random variables, you get a gamma distribution. Then when you square a normal random variable, you get a gamma with some alpha, some beta. Cauchy distribution is simply one normal divided by another normal. Okay, gamma and beta are also related in some way. Okay, then sum of independent gamma is gamma of n alpha times beta. So I have just listed. I just want you to know that there are some kinds of relationships between all of these distributions that we saw before, all of the continuous distributions, and you can have a look at them and maybe try to have idea about at least a few of them, so that it can be handy in solving problems. It will come very handy. Okay, so here we have one problem related to center limit theorem. So some company produces 600 bottles daily. If a bottle is selected uniformly at random, then the probability that the bottle is of good quality is 60%. So it is actually the underlying distribution, okay, because uh, it is kind of talking about the full distribution. Now you have to answer a question using center limit theorem. We have to find the approximate probability that the machine will produce more than 370 bottles that are of good quality on a particular day. Okay. So daily what happens, the company produces 600 bottles, but some of them are of good quality, some of them are of bad quality. Okay, and that number, the number of bottles of good quality varies. Okay, so the question is to find, how do you find the probability that that a machine will produce more than 370 bottles that are of good quality on a particular day. Okay, so generally, if you want to solve this kind of problem, you will have to use what kind of calculation you have to use. Can anyone tell me? How will you find this kind of problem if you are given? So suppose you don't know about center limit theorem, anything, and you don't know anything about center limit theorem. How will you solve this problem?
So we can solve this using binomial, but the calculations will be huge.
Yeah, correct. So computations will be very, very huge for this, but this is the power of central limit theorem. Okay, we will not get the exact probability, but the precision that we will get will be not that bad. So what we will do, we will first write probability that x being greater than 370. So then we will try to standardize this. So for standardizing, we will subtract the mean. We are aware, okay, we are aware that it follows a binomial distribution, but still we are not using binomial distribution. So from binomial distribution, we are calculating the mean of x, dividing it by the standard deviation, okay, sigma squared, n sigma squared. Okay, so the central limit theorem comes at this point. It says that this follows a standard normal distribution, or even x follows a central normal distribution, but with different mean and different variance. But this is a standard normal distribution. Okay, now if you do this calculation, we can simply use the standard normal tables to calculate this. You will find these values in the exam. Okay, no need to worry about that. Then here I have included one more question related to the moment generating functions, because it was also important. So it is a very typical uses of what moment generating functions is. So you have been given a simple random variable, discrete random variable with certain PMF. Okay? And what you have to do is you have to find the moment generating function of the random variable. Okay, so you have been given another random variable y, which is just the summation of x1 and x2, where x1 and x2 are just IID of x. These are the same random variables but independent and identically distributed. So we have to simply find the moment generating function of the random variable y. So how do you find the moment generating function of m5? You remember we had this in slides, right? So you will just multiply. You will just multiply the moment generating functions of the two random variables. But since both of them are identical, we can write this. The MGF will also be the same, because MGF is just the expected value of e raised to the power lambda x. Right? So it will just be this squared. Okay. And how do you calculate the MGF of x? You just multiply the function. What is the function? Function is e raised to the power lambda x. Okay. So e raised to the power lambda times 0. So it becomes 1 times the probability of that x. So 1 by 4. Then 1 by 2 times e raised to the power lambda x. So 1 by 2 is corresponding to 1 plus 1 by 4 times e raised to the power 2 lambda. So this is how you get the MGF of x. Then to calculate the MGF of y, what you do is you just square it and you will get it. So there can be one more question from this. So you have been given this, or suppose there can be one question from here that you have been given the moment generating function of y. How do you find the distribution of y? Can you plot it? Can anyone explain me how do you read the distribution from this? It is very simple, but I want it to hear from you. Anyone?
So probability of 0 will be 1 by 16. Probability of 1 will be 1 by 4.
Okay, so I think you have got the idea, right? So this is just the probability, and whatever you have as the coefficient, it is just the value that is taken, right? So this is how you read a distribution from the moment generating functions. And if you have been given a moment generating function, if you have been given a distribution, you can write the corresponding moment generating function for this. So this is a very simple exercise that you must be comfortable with. Then coming to week 9, we have parameter estimation. Okay, so up to now we have been given mostly we have been given the parameters of a distribution. Okay, and we have to find the probability related to some event. But from this week, in this week and week 9 and week 10, we study about parameter estimation. When you are not given the parameters of a distribution and you are just given samples, okay, then how do you come up with what is the what are the parameters for the distribution? So suppose I give you a dice and I don't tell you what is the probability that the dice will take value 1, what is the probability that x will take value 2, 3, and so on. But I just give you a sample that I tossed it this many times and these were the results. Then how do you come up with what is the parameter of the what are the probabilities of each of the phases? So that job is yours. So what you will do, you will define an estimator and then use that samples, and then you will use that samples that will output some parameter. So that is generally called the estimator. So estimator, what is an estimator? Estimator is simply a function of the samples. So whatever samples I have provided to you, you will define an estimator. Estimator will take as input the samples and it will output theta, the unknown parameter that you're trying to calculate. Okay, theta hat is a function of n random variables. I hope these things are very compatible for you. Then there is something. Then there are a lot of things that we do to make sure that whatever we are doing, whatever the job of parameter estimation we are doing it in a good way, right? Because I give you a sample, and it's not necessary that you will come up with a good parameter, good guess for the parameter. Okay, so how do you assess the quality of the estimate that you get? So for that, we have a lot of measures. For example, we have estimation error, that is simply the uh, the estimator minus theta. Okay, how much your estimate deviate from the actual distribution data, but we have just put it here so that we can get the error. Okay, then uh, since you should also note that theta hat, that is your estimator, it is also a random variable. Okay, because it can give different values for the different samples. Depending on the samples, it can give different values. So it is a random variable. So in a similar way that we described Chebyshev's bond for other random variables, we can talk about Chebyshev's bond for this estimator. Okay, so that's what we have done here. So error is our random variable of choice. Okay, so we're trying to measure the error. Okay, how much? So at this point, Chebyshev's bond makes some sense. So you don't want the error to be greater than some value. Okay, or you want the error to be confined within some range. In that case, you will use Chebyshev's bond to, so you can confidently say that I am 95% confident that my error will not go beyond something like 5, some units, some delta. So then we had bias and risk. So bias is simply expected value of the error, and it is bias. It is called unbiased if it has a bias 0. Then we have risk. So these are very simple definitions. Okay, it is mean squared error, then variance of estimator. So because theta hat is a random variable, it is just you can how do you define variance for a random variable. So it is not different. And one thing to note here is that variance of error is equal to variance of theta, because error is just the translated version of theta. Theta hat minus theta is the error.
Sir, if my bias comes out to be non-zero, then it is then it is biased.
Yeah, correct.
Only when my the estimator. Sorry.
Yeah, when it is 0, we call it unbiased.
Okay.
Sir, please clear bias and unbiased.
So what are you trying to do? You are trying to come up with some estimator which will output some kind of estimate for the parameter. But some estimators are good, some estimators are not that good. Okay, so for that we have some measures. So if we have, what you would like is an estimator with low error. okay, low error, and which is unbiased, okay, with which has bias 0. So bias is simply expected value of the error. Okay, so whenever you calculate the expected value of the error, it will give the bias for theta hat. And if it is 0, it means it is unbiased. So you would like your estimator to be unbiased always. Okay, and you also want your risk to be low. Variance also you want it to be low. So there are 4 things that you worry about when designing an estimator. Okay, there can be infinite number of estimators for any parameter, and all of them will have different properties, okay, and different quality. So we studied about 2 methods of parameter estimator design. The first was method of moments and maximum likelihood estimator. Before going into that, there is one more thing called bias variance trade-off. Okay, so what is this? So as I told you that what you want is a very good estimator for your parameter, but and you want to keep the bias low, variance low, risk low. You want to keep everything low. But what happens is when you the estimator which has low bias, which is unbiased, will have high variance, or it will have high risk. So this is called bias variance trade-off. So okay, so either you have to mm, accept high bias or high risk. Okay, so these things are interrelated. So when you're trying to decrease one of them, it will affect other. So that is what this relationship is trying to do. Then we had 2 kinds of estimation methods: method of moments and maximum likelihood approach. So I think these things are very simple. Method of moments, what we do, there is something called moments. What are moments? Moments are simply expected value of the random variable. So expected value of x is simply the first moment. Expected value of x squared is simply the second moment, and so on. Okay. So there is something called distribution moments, and there is something called sample moments. So suppose I give you a sample of I have got a die from somewhere. I don't know what are the values of uh, probability that each face will land. So I just what I do, I just throw it certain times, 10 times for example, and I get something like this: 1, 2, 5, 6, okay, 3, and so on. Suppose I throw it certain number of times, I get this sample. Okay. Now I need to calculate. Suppose I want to know the what is the mean of the value. Sorry, mean of this, mean of all the values. Then the mean that you calculate from the sample, that is called the sample moment. Okay, it is denoted by small m1. So small m1 will just be how many times you get this divided by 1 times how many times you the probability of getting 1 from your sample, and so on. Okay, m1, m2, m3, and you equate it with capital M1. Sorry, yeah, capital M1. Okay, you reverse this, and then you will get the estimate for your estimator for your case. So we will see one example where you can do that. So the main goal of this exercise is to equate distribution moments with sample moments, and then we will solve for theta. Okay. In maximum likelihood estimation, we define likelihood function. Okay, what is the likelihood function? It says that what is the probability given a theta? We assume theta has a certain value, and then we try to know what is the likelihood that this sample was observed. So for that, what we do, we multiply the probability of each of the sample points given that theta. So we get some likelihood function, and we try to maximize it. Okay, so one method of maximizing or minimizing a function, that is you take derivative of that, set it to 0, and then you get that value. But generally what we do, since it is just multiplication, so a lot of multiplication will be there. So what you do, you generally take log so that all of them comes in plus, and then you do the optimization and you find the value of the parameter. So here we have an example. So let x be a discrete random variable with such that x is 0 and 1, and we have been given the probability of x taking value 0. Okay, theta is an unknown constant. Consider a random sample. This you have been given this sample. You have to find the method of moments estimate of theta for the given sample. Okay, so how do you do this? We first calculate the distribution moment. Distribution moment is simply the probability. The moment calculated from the moments. You remember it. Expected value of x, expected value of x squared. These moments calculated in terms of the distribution parameters, or distribution in terms of the distribution, actual distribution. So expected value of x is equal to this. Okay, and so since we have just one parameter as unknown, we can just use the first moment. So first we will calculate the first moment, first distribution moment, and first sample moment. So distribution moment we know. Okay, expected value of this is just equal to 0 times this times 1 times 1 minus this. So this is your distribution moment. But what is sample moment? So sample moment is simply 2 by 5, because you add all of them divided by 5, you get. So what I have done is I have just equated both of them, and you get the value for the parameter, unknown parameter theta. So theta comes out to be 0.25. I think all of you are comfortable with this method, is it? Once you understand it, very easy. Okay, so moving on to the next question. Here we have something related to maximum likelihood estimation. Okay, so the same problem statement is there. We have been given the probability of x taking value 0, and we can calculate the probability of x taking value 1 also by just subtracting this quantity from 1. So but we don't know about the parameter. Okay, and we have our job is to calculate find the parameter or estimate the parameter. So what we will do, first we will find the likelihood function. Okay, so we don't know theta. Okay, but we don't know what is the actual value of theta, but we consider that it is some value. Okay, theta. So this is a sample that we are given, and what is the likelihood of observing the sample? You will just multiply each of the probabilities. So what is the probability of getting 1? What is the probability of getting 0? So you will multiply all of them, you will get the likelihood, right? Because all of these are independent. So you can just multiply all of them, you will get the likelihood function. Likelihood means nothing but just the probability of observing this sample. So 0 appears 3 times, so the probability of 0 multiplied 3 times probability of 1 multiplied 2 times. So then we just drop the constants, because this does not affect the optimization problem or maximization or minimization. Okay, so then we take the log, because suppose you want to differentiate this function, how tough it will be. So if you take the log also, the answer won't be affected. So you take the log to differentiate it, set it to 0, and then you will get the answer. Okay, so I have just differentiated it here, set it to 0, and then we got the value of theta as 0.25. So I think there will certainly be 1 or 2 questions from this in the end term. So you have to be comfortable with this. Okay, then we considered Bayesian estimation. So the two methods that we learned that were called frequentist approach. Okay, frequentist means you get a certain particular value for that. Okay, but you don't want any particular value for the parameter in Bayesian estimation. Okay, so what is Bayesian estimation? In Bayesian estimation, we are using Bayes rule. Okay, the context in which we are using that is different, but basically we are using Bayes rule. Remember that. Okay, a method of estimation where all uncertain quantities are modeled as random variables. Okay, so parameters we don't consider them as when we do the Bayesian estimation, you will not get some particular value, but you will get a random. But you can get some value in a range because you are considering that as a random variable. Okay, so that's why you see here that capital theta is being used. Is capital theta. So we represent random variables with capital letters. So that's why here theta, capital theta we are considering because we are considering the parameter as some random variable. Okay, so here if you observe here, okay, now the main feature of Bayesian estimation is that it uses something called prior. Okay, what is prior? Prior is simply some previous information about the parameter that you are trying to estimate. Okay, in the frequentist approaches, maximum likelihood and method of moments, we did not consider any such possibility. But here we are trying to look if we know something about the distribution of the parameter. Okay, we incorporate here in our calculation. Okay, so what we do, we just use the Bayes rule here. So probability that the random variable theta, that is our parameter, will take value some exact value theta given the sample, it is proportional to. So what Bayes rule says? It says that we will flip this. Okay, so probability of sample given theta equals theta times this. So this is called the prior. So you are utilizing some previous knowledge about the parameter, and this is called likelihood that you already know. Likelihood. Okay. So what is likelihood? You consider some theta, and then you try to calculate the sample probability of or likelihood of observing that sample. So that is exactly likelihood times the prior. Prior is simply what you know about the distribution of this. Okay, and then yeah, I have discussed the prior, and then what you get out of Bayesian estimation. When you do Bayesian estimation, you don't get a particular value. You get some distribution. Okay. You get some distribution about you have some prior information about the distribution of the parameter, and as an output you also get some distribution that is called posterior distribution. Okay, so this is what you get. Probability of theta given theta is equal to theta given the sample. Okay, so you will get something like there are two possible values of theta. Okay, so in method of moments approach, you got just one value. Suppose mean of this is 4, something like that. But Bayesian estimate will give you certain probability, certain possibilities. It can be 4 or 5. Okay, 4 had some probability of happening, 5 had some probability of happening. So these kind of things you will get in Bayesian estimation. Okay, then we got posterior mode and posterior mean in case of this. Okay, so then we did multiple kinds of Bayesian estimation for different examples, and we got certain results that these are just part of the lectures. You can go through this, and then we saw something related to geometric and Poisson samples. Okay, so these are just simple examples that were there from the lectures. I have summarized them in the slides, so I don't need to go through all of them. The main things I need to discuss here. Okay, then I have some problem related to this. The number of claims received by an insurance company during a week follows a Poisson distribution. So this is our prior distribution. The weekly number of claims observed over a 10-week period are this. This is our sample. Assume the prior distribution of lambda to be gamma of 5,1. Okay, so Poisson is not the prior. This is prior is gamma of 5,1. Okay. We have to find the posterior distribution of P. So posterior is simply likelihood times prior. So likelihood, this is simply probability of observing the sample given capital theta is equal to small theta. Okay, so what is the probability of observing the sample, since it follows a Poisson distribution. Okay, we assume it's the parameter is lambda, and you multiply all of them, you get the likelihood of the sample times prior. Prior is simply beta gamma distribution of alpha equals 5, beta equals 1. So this is what you get as prior. And then you multiply, you get this expression, and you observe that it is gamma of 40 comma 11. So you get posterior distribution, you don't get a number. So this is your answer. But later you will be asked to calculate the posterior mean. So mean for gamma distribution is simply alpha by beta. So you do that. Okay. There is something also called posterior mode uh, that will also be there sometimes. Okay, so when you get some more than two possibilities, there are some probabilities associated. There are some probabilities associated with each of the values, and I think, I hope you remember that. Okay. Then the interesting and most important is hypothesis testing, that is there in week 11 and week 12. So you have some assumption about some distribution or some random variable, and you want to verify that using samples. Okay. Wait for a minute. Okay, so yeah, hypothesis testing is all about testing your hypothesis. So there is null hypothesis and alternative hypothesis. Okay, null is something that is, that is very new. Sorry, that is a very traditional kind of thing. Okay, it's not something new, but generally, the alternative hypothesis is something that is new. Okay, that has come from some research or something. Okay, then we discussed something about type 1 error. We have something type 1 error, type 2 error. So these are very basic definitions that you must be compatible with. Okay, so type 1 error occurs when the null hypothesis is rejected, okay, even though it is true. So you know the notations for that. Then type 2 error, it is beta. Type 1 error is also called the significance level, that is determined by alpha. Okay. So these are very basic notations of the basic foundational things about hypothesis testing. Okay. Then we have simple hypothesis, composite hypothesis. In simple hypothesis, we specify the exact distribution of the sample, right? So for example, you make an assumption about the mean of the height of the students in a class. You say exactly it is equal to this. But in composite hypothesis, we don't say that exactly, but we say that it is in some range. In that case, it is composite when it takes more than one value. And we have some testing methods. So there are actually, I think, 4 testing methods that are central to week 11 and week 12. So there will certainly be 2 to 3 or even more questions from this part. Okay. So the first and one more important thing is p-value here. So the first kind of question can come where you are asked about the understanding of basic things about hypothesis testing. For example, significance level, power of a test, okay, type 1 error, type 2 error, this kind of things. But then one question might come about how do you calculate p-value, or when you are given some p-value, how do you come to a conclusion about this? Okay, then standard testing methods that are the bread and butter of this thing. So that is very obvious. Okay, so types of jet test. Okay, so what is a jet test? Can anyone uh, unmute and tell me? Okay, so what is a jet test? Jet test is a simple hypothesis testing method, okay, that is based on normal distribution. Okay, so we assume there is something called null distribution. So when you assume the null hypothesis to be true, under the null hypothesis to be true, we get some distribution. Okay, and we make some assumptions about that, and we decide ourselves, okay, based on a significance level. Suppose we decide that we want to be 95%, alpha is equal to 0.95. It means we want to be 95% confident about our whatever decision we are making. Okay, it is a significance level. What is the significance of our results? Okay, so if we decide, first of all, what we do, we decide alpha. Okay, we decide alpha, it decides what kind of tests we are going to do, or what kind of thresholds are going to be. So it decides the critical value. Okay, based on this we will reject or accept a hypothesis. Okay, so in week 11 there was just the basics of hypothesis testing and just jet test. Okay, so these are the two things of week 11. So here we have been given 100 samples. All of them are normal with mean mu, and that is unknown, and variance is 16. We have been given null and alternative hypothesis. So we don't know mu, and we want to uh, hypothesize about what are the values that mu can take. So one hypothesis says that mu is equal to -1. So one of you said, suppose mu is equal to -1. The other one of you says mu is equal to -1. Now, whom should I believe looking at the sample? Okay, so that's our job of hypothesis testing. Which of the hypothesis is correct? So there is something called test statistic. Okay, we calculate test statistic from the samples, and if they based on the test statistic taking some value, we come to a conclusion. Okay, so consider a test. Test is also defined that rejects is not if t is less than c for some constant c. What is the power of the test in terms of c? But so what is power? Power is just 1 minus beta. Beta is just the type 2 error. Okay, so type 2 error is simply accepting it's not given, HA is true, alternative is true. We are accepting H not while HA is true. That is type 2 error. But 1 minus beta, power of it is simply the opposite of that. So reject H not if HA is true. So simply you have to denote it in probability notation. Rejecting H not means T less than C. Okay, given mu is equal to -1, since alternative is mu equals -1. Okay, so you have to use mu equals -1. So the complete distribution. So it can be called the alternative distribution. Okay, so then you simply okay, what is the power of a test that you have to calculate? Okay, so what you do, simply you use mu equals -1 and you calculate this. Okay, so based on the significance level that you will choose, or the critical value, you will get the value of power of the test. But since we are not given the significance level, alpha or critical value, we will just describe it in terms of C. Okay, then we have one more problem. So here we have to find the p value. Okay, so p value is simply the probability of rejecting samples more extreme than the current one. Okay, so what happens? Suppose there is some experiment, okay, and you got some result which is very, very rare. Okay, then you can be doubtful about whether your experiment was good or not. Okay, suppose for example, you measure the height, or you measure the weight of a person. You measure the weight of a person. of all the students in a class. You go to your home and you see the weight to be 250 kgs. Okay, so you will feel like, oh, I don't think 250 kgs can be the weight of any person in this class. Okay, so that seems like a very rare event. Okay, so you have some samples, weights of the students, and you see one sample. Okay, so that is your sample, and based on that you want to come to a conclusion. So p value is related to that. Okay, so p value is simply, you define that, suppose there are two hypotheses about the weight of the students in the class. One says that weight of the students is equal to 70 kg. Okay, and the other one says that it is greater than 70 kg. Okay, so null says that it is weight is equal to 70. The other one says alternative is equal to weight is equal to greater than 70. Okay, now at which point, there is a limit to this greater than 70. Okay, so if it is greater than 70, then you will generally accept the alternative, but there is a limit to this, right? So that's what we do here. So what's the sample that we have? We have the sample standard deviation. So we are here, what we are doing, we are assuming about the mean. Okay, we are testing the mean here. Okay, so suppose the mean and the standard deviation of the given samples are this. So mean is 36.9 and standard deviation is this. Then if our mean is greater than test statistic is greater than 36.9, given null is true, in that case we will reject the null. Okay, so that's how you calculate and you get the value this. Then in week 12 we have some more tests that are there in week 12. So the three tests are chi-square test. Okay, then no, first you have t-test for mean, then you have chi-square test for variance, and f-test for comparing variances. So in z-test, what you see is that you know the variance, but you don't know the mean. Okay, but here you are testing for the mean, but you don't know the variance itself. So where do you calculate the variance from? You calculate the sample variance. You use sample variance here, and it is very similar to very similar to z-test. Just the difference between z-test and t-test is that in case of t-test, you use the sample variance instead of the distribution variance, and the process is very similar. You are testing for the mean. Okay, then in chi-square test for variance. Okay, so chi distribution, it is just 1 n minus 1 is squared by sigma naught squared. So if you have a distribution, okay, which has a distribution variance sigma naught, and you have collected a sample, n samples, then n minus 1 times s squared by sigma squared, it follows a chi-square distribution with n minus 1 degrees of freedom. Okay, so the argument for how do you reject null or how do you accept null, these things are same for all the tests. Okay, so you have to understand the fact that whatever type of test you do, either it is z-test, if you understand one test, then you will be able to understand all of the tests. Okay, if you understand p-value for one test, alpha, so if you understand the basics of test for, so first try to understand z-test. Okay, if you understand z-test, that is the very first test, then you will be able to do all the tests. Okay, so all of the tests have some very basic terms like alpha, critical value, okay, test statistic. So always you will find the test statistic. If it is greater than c, you will so suppose you have null at some mu equals mu naught, and you have alternative as mu greater than mu naught. Okay, then when you are doing the test, you will reject the null if t is greater than some value c, because in whatever form is the alternative is there, you will keep it. But this is one case. Okay, in the second case, suppose your null is mu equals mu naught. I am giving you example of all of the cases in you can get the problem. Okay, you will have problems, and all of these will have at least one of these cases. So mu is less than mu naught. You can take any example and try to understand this. Then you will reject the null if t is less than some critical value. And how is it? How is this c defined? It is defined by sub alpha, based on how confident you want to become about the test. Okay, so it is corresponding to some alpha. So how do you do the test? You first choose some alpha, how much confident you want to be about the test. Then corresponding to this you will get some critical value. Okay, you calculate the t. What is t? T is simply the sample mean. Okay, don't think about it like it's some a strange thing. It's sample mean. If you are doing the test for the mean, then it is just sample mean. So you calculate the sample mean. If it is less than some critical value that comes from the amount you want to be confident about. So suppose you want to be 95% confident, then you will get some value of c. And if that sample mean, if your sample mean is less than some that value, then you will say don't. Yeah, is there confusion here? Okay. Okay. So this is the point I wanted to make here is that all of the tests are similar. Okay. Even for the chi-square test, the same thing holds. Just what is the difference? But what's the difference? Difference is that what is the distribution of the test statistic that matters. Okay, distribution of the test statistic is different, and that should not matter for you, right? That should not matter for you, because look here, what we are doing here, we are testing if the test statistic, okay, what we are defining here alpha, and that is same for all of kinds of distributions. Either it doesn't matter if it is a chi-square distribution or f test, we define it in the same way. But you have to understand what kind of a distribution is chi-square and everything set. So my suggestion would be to understand at least one test carefully and then generalize it to all the tests. Okay, so try to understand at least one test. So Z test and T test are very similar. Then we have chi-squared and F test. So F test is done for variances. Chi-squared is done for chi-squared and F test are both done for variances. Okay. So in F test, what we have two random variables. Okay. We have two samples, and what we do, we take the, so there is one thing I forgot to mention. There are two kinds of tests in this. Okay, the first kind of test is called one sample test, where you just consider one samples, and there are two sample tests like chi-squared and f test. So in chi-squared also we are considering two samples. Okay, so here we have two samples, and we are what we are doing, we are just dividing the test. What is our test statistic? It is f, which is simply the sample standard sample variance of both the samples. Okay, so that's why it is a two sample test, because we are taking two samples and we're calculating the variances for both of them. We are dividing them. So here what would be our null hypothesis? Null hypothesis is that both of the sample variances are same. And what is our alternative hypothesis? Alternative is that both of them are not same. Okay, so when we are defining this test statistic, we would first, what we do, as I said, you would want to be want to specify how much confident you want to be. So suppose I want to be 95% confident about my result. Then corresponding to this, you will get some value of critical value. So if the value of f comes out to be 1, you take two samples, you calculate the variances, you divide them, you get the value of f equals 1. It means you accept the null. But when do you reject the null? You reject the null when f is greater than the critical value. C comes from this. Okay, and AP is simply the difference of this, or AP is less than some value of C. So all of the tests are same unless you get what they are doing. Okay, so here is a simple problem based on this. I think it's chi-square test. So a chemical company produces a certain drug whose weight has a certain standard deviation 5 mg. Okay, a new method for the production of the drug is introduced involving some additional cost. So new drug is being introduced, and management will authorize the change in the production technique only if the standard deviation of weights in the new process is less than 5 mg. Okay, a sample of 10 drugs for the same is chosen, and the standard deviation in the weight is found to be 3.38. So the first thing you should note is what kind of a test this is. So this is about chi-square test. Okay, you have old drug and you have a new drug. Okay, so when you are producing the old drug, then the standard deviation in the weight is just 5 mg. Okay, and when you're trying to make a new drug, then it will have some different amount of standard deviation. Okay, what's the null hypothesis here? Null hypothesis will say that the drug will have sigma equals 5. Okay, and okay, so identify the null and alternative hypothesis. So you have to see what is being claimed by the new thing. Okay, so as I said before, uh, whatever traditional thing is there, okay, you consider that under null hypothesis. Okay, so the old case you consider under null hypothesis, and the new drug you will consider under alternative hypothesis, because that is something new that is being implemented. Okay, so read this line: management will authorize the change in the production technique only if the standard deviation of weights in the new process is less than 5 mg. Okay, so if it is less than 5 mg, then it will authorize it. So it means it is alternative. Okay, so this is your null hypothesis and this is alternative hypothesis. A sample of 10 drugs for the same is chosen, and the standard deviation in the weight is found to be 3.38. Should the management authorize it or not authorize it? That is the question that you have to answer. So as usual, you have to first consider how much confident you want to be about the result. So here it's already given alpha is equal to 0.05. It's okay if you are only 5% confident about it. So corresponding to this, you will get some critical value. You will compare this critical value with this value 3.38. Compare with. Okay. So this is what you do. Okay. So alpha is simply given as this 0.5. From here, what we have to calculate? We have to know the critical value, right? So we find the critical value as 9.236 corresponding to the alpha. Then what we do? Then we try to compare this value of C, critical value, with S squared, the sample we are given. Sample of 10 drugs for the same chosen, and the standard deviation in the weight is found to be 3.83. So S squared is 14.767. So it is less than, is it less than C or it is greater than C? So look at the alternative. We will reject the null if it is less than. Okay. So the sample standard deviation, it is greater than, right? So it is not less than C. So if it would have been less than C, then we would have rejected the null, right? Because here we have written it would reject the null. Yeah, because it is, if it is less than this, then we would reject it. But we want to, but it is not less than, it is greater than, so we will accept null. Is there any confusion in this? So this is the last problem that we have. So yeah, this was all. So this was all about stats 2. Okay, so beginning to end.